studying in medical physics in Bangladesh and working at the South Asia Center for Medical Physics and Cancer Research. I am with you as a moderator of today's program. Good to see you again. Today our honorable speaker is Dr. Frank William Hensley, who was the speaker yesterday also. Well, pleased to inform you, this program has been accredited by the International Organization for Medical Physics as CPD event for medical physicists with 22 CPD credit points. This is to inform you that there will be an examination at the end of 8 lectures with practical session and group discussion. You must pass the examination for certificates with CPD points. Otherwise, you will get attendance certificate only. Before we start, I remind you that your question or any comment type in the chat box. We'll pick up your questions after the lecture. And kindly mute your microphone and stop your webcam. No more delay. Today, the second lecture is on source calibration, verification, and dose measurement. Now, I am inviting Dr. Frank Hensley to deliver your talk. Are you ready, sir?
All right. Yes, thank you very much. I'll pop up my screen. I think I'm ready for that. Yes, coming.
It's okay, sir.
Okay, you should have it in a second. I'll have to, okay, I will have to change my presentations after a few slides. That will make a short break. Let's see, maybe I can prepare for that before we start so that I have everything ready. Will this work? Just a second.
Sure, sir.
Okay, so that seems to work. That's not what I want. Here's where I want to go. Okay. Okay, so now I'm back and I think I'm ready. Can you hear me? Everything okay? See
yes,
my
sir.
slides? Okay, fine. Okay. Okay, I'll start from the point where I ended yesterday, and that was about the next topic would be speaking about brachytherapy source calibration. I just want to remind you of two things from yesterday's lecture. We will be speaking about kerma, the sum of the kinetic energy of the interacting particles only stemming from particles from primary radiation, which are entering the considered mass element, and dose, which is the total energy absorbed by material, which includes also the energy from scattered radiation from the material surrounding the considered volume. So these are two different things. And in our dose calculations, we actually, in most instances, use kerma. That's the one thing. And our source specification, the number with which we account for the activity of the source that will decay with radioactive decay. We use the air camera rate, or specifically the reference air camera rate, to do this, and not the activity. So these are two things that we'll be using frequently today. Okay, when you purchase a radioactive source, you will get it with a calibration certificate. That looks like this, and this calibration certificate will tell you the numbers that you need to feed into your treatment planning system, and also to calculate the dose. First of all, it specifies the source. Which source are you actually using? So you get the serial number of the source, so you can identify it correctly, and also the production code that tells you which type of source it is, so you can use the correct data for this source. And then for this specific source that you are getting, you get information on the calibration, that is on the reference air camera rate of the source measured at a certain date. So you can calculate the present air camera rate from the radioactive decay, and it also gives you, well, I guess all of them do, they also give you information on the apparent activity that is connected with this reference air camera rate. But you use the air camera rate in all the calculations. Okay. In all countries that have regulations on these topics, there is a regulation which obliges the which asks for the verification of the air camera rate before the first application of the source on a patient. So when you receive a source, the correctness of the manufacturer statements, the ones that I showed you of the reference air camera rate, must be verified, and they must be verified immediately after delivery of the source, before the first application on a patient. And the regulations also say this must be done by a qualified medical physicist, not just by the janitor or whoever gets the source at the door. So this is a requirement in almost in all countries that have regulations on medical physics. A second thing that most regulations also require is a second check of the air camera rate. And you do this for iridium source maybe 2 weeks after you receive the source. And the idea of this is that by measuring it at 2 different dates, you can check the radioactive decay. Has the source activity, has reference air camera rate really decreased as it would be predicted by the radioactive decay? If not, you must consider if there's possibly some kind of a contamination, some other radionuclide in the source, which changes the decay rate. So this is a second check that you should also perform. The calibration of the source is, well, we use the air camera rate, and the calibration of the source, as it is performed in the standards lab, any calibration must be traceable to the calibration in a standards lab. And the calibration at the standards lab actually happens as a measurement of air camera rate. And it's a so-called free in air measurement, which means that the source, well, it's measured by an ionization chamber at a large distance, something like 1 meter away. And it's free in air means that it is a measurement with as little scatter as possible, so that you can actually really measure only the radiation interactions which happen in the active volume, in the sensitive volume of your ionization chamber. So free in air measurement of the air camera rate, and at 1 meter is where our reference air camera rate is defined. So it would be measured basically at 1 meter or at some other distance that you can recalculate by inverse square law. But it must be at a large distance from the source. This is a rather difficult setup to do. Simply positioning of the source and an ionization chamber exactly at 1 meter distance is a complicated affair that you can't so easily do. And also providing the free in air situation that you have low scatter is also not that easy. You need a big room, and all your measuring devices need to be far away from any scattering material, that is the walls, the afterloader, whatever. Okay, to reduce or to correct for a scatter that still happens, these sources are normally then performed with a shadow block, or a second measurement is performed with a shadow block, which blocks the complete source so that your ionization chamber is measuring only the scatter from the walls. And then the difference of the measurements without scatter block and with scatter block will give you the correct air camera rate. So this is how the standards labs actually do it. And this here shows you the set up at the German standards lab, Physikalisch-Technische Bundesanstalt, PTB. And it's fairly complicated. This here is a, oops, let's go back. This here is a self-made afterloading machine with the electronic devices that they have. This here is the radioactive or the lead vault in which they store this the source. Up here, this is a collimator, and this large sphere here is the ionization chamber. And to get a correct positioning, what they use is an industrial robot so that they can very exactly position the source. So this is quite a big setup, but otherwise it works exactly the way I just showed you. To measure the air camera rate, you use an ionization chamber, so you need a formalism that similar to, or it's actually the same one that you know from TRS 483. And this here shows you the equation that you would be using. And I won't go through all these numbers here. I'll go through a very similar equation to calculate the dose. It's actually, this is just a rearrangement of the equation that I will be explaining. But you need to know all of these parameters here, and they are all sources of uncertainty. So it's quite a complicated affair, and it's not something that you would want to do in the hospital, because it's simply too much effort to make such a measurement. But you could do it, and this equation here shows you how you can measure air camera rate with a source, with an ionization chamber, which is calibrated in terms of absorbed dose to water. So you have to recalculate from absorbed dose to water to air camera, and you can do this with all of these corrections and factors that are in this equation. So I'll just click through this. I won't explain these things, but as I say, they'll be in a further equation, and you can look at these numbers later on and see if you understand how it works. At the hospital, you have a different method of measuring, and that is using a well chamber, or a so-called re-entrant chamber. And this is what you see on this slide here. A re-entrant chamber is basically, it looks like, well, this is what an old type looks like in reality. And what it actually is a large cylindric pot with double walls and with a void space between the two walls. So this is a double cylinder, and you have a hollow between the inner and the outer wall of the cylinder. And inside this volume, this is an air volume, you have a collection electrode, like an ionization chamber, so that this complete volume here in this cylindrical cylindrical body acts as an ionization chamber. And now you can place your source inside this, and what happens is that all the radiation that is emitted from the source is seen by the ionization chamber, except for the top here, for the lid. But you get an information on the total amount of radiation which is emitted from the source. And this chamber is then cross-calibrated to air camera rate, which is done basically by making a measurement, just like I showed it. And then immediately after that, you make a second measurement using your ionization chamber, and you calculate a calibration factor from the ratio of these two measurements. Another way to do it would be to have a measurement with a second well chamber, calibrated well chamber, with which you know the calibration factor, and then you take your new well chamber and make a second measurement, and from the reading you can then calculate the calibration factor of the new chamber. That is also a possible way to calibrate a well chamber. The important thing is that this calibration chain must be traceable to the calibration by the standards lab. So your well chamber that you use to compare with must be calibrated by the standard lab or one before that. Okay, and then this the well chamber is calibrated in terms of reference air camera rate, or for use in TG43, with which we'll speak, it is calibrated in source strength, SK. I'll show you what that is later. And something that you need to know is that you perform your measurement at the sweet spot. There is in the positions that you can place your source here in this insertion jig. There is one position in the chamber which gives you a maximum current, and this is the place where you calibrate. So these are the things you know, and then it's actually very easy to verify your calibration. So that's how it goes. This here gives you some literature on the verification of the air camera rate. These are things that you should have if you perform brachytherapy, and here's where you can look them up. The important document, the most important, is here this Tech Doc 1274 by IAEA, which describes the calibration process both by the standards laboratory and by the user in the clinic. These German and Swiss recommendations are actually also published in English, so you might want to you might look into those. And you can also look into double APM task group reports like TG56. Okay, so I think that was it. I'll summarize what I was speaking about yesterday and right now. Brachytherapy exploits the steep one of our square law to close to the source to create small dose distributions surrounded by a steep dose gradient. The main application method is afterloading technique, and for special applications, also seeds are used. The main special application for this is prostate cancer. Brachytherapy is in principle labor intensive, but external beam radiation, external beam therapy is actually labor intensive too. So if your hospital administrator says brachytherapy is too intense, costs too much labor time, compare what time you need to generate a plan, to do all the segmenting, to verify a plan, and all of these things, and you'll come up with very similar times as you use in brachytherapy. The key application of brachytherapy worldwide is cervical cancer. And something I didn't say, but something you should know, is that if you apply brachytherapy correctly for cervical cancer, it has results that are just as good, comparable to any other treatment modality, to surgery, to internal medicine therapy, and so on. So if you have poor access to surgery, you can do just as good with brachytherapy. And that, I think, is an important message for, especially for remote regions in lower income countries. Brachytherapy then can be expanded to a large number of applications, and these are especially for sites which are difficult to treat with external beam therapy, for instance, recurrences. So you can do more with brachytherapy than only gynecological brachytherapy. Something I'm trying to show you in these two lectures is you need basic physics knowledge to understand the properties of brachytherapy dose distribution. And if you don't understand them, you can't really judge well, where the limits are, what things you shouldn't be doing, and what things you shouldn't be calculating with for brachytherapy. Okay, and what I just now spoke about, the source strength is specified by the source's air camera rate, and it must be qualified by a qualified medical physics. It must be verified by a qualified medical physics before application. So I think that was this. Okay, questions a little bit later, and I'll switch to my other presentation now. Find the right one. Should be this one here. Not quite yet. This here. Okay, so now I would like to speak about dose calculation for brachytherapy. Mouse here.
So kindly try to complete your slide timely, because we have time.
Okay, I'll rush through a few of these things here. There are some things that I think you need to read that I can't really explain, and I'll just show the slides and show you. They show the references where you can read up these things. Okay. So the objectives of this presentation is to understand the physical steps. How do you actually calculate dose from a brachytherapy source? How is it done as a physical procedure or as a physical calculation? And then how is it actually done in your planning system? And the planning system doesn't do it the way I'm going to show it first, but it uses this this TG-43 formalism. And you should need to understand how this TG formalism works and how it is applied for dose calculation. And I also would want to show you the limitations of the TG-43 formalism, which are actually not many. Okay, now comparing external beam therapy and brachytherapy, there's something different. In external beam therapy, you are used to measuring your data from your accelerator. So you'll have an accelerator with a source up here, and you will measure the data in a water phantom down here with an ionization chamber, and you will measure this at about 1 meter distance. That's the distance that you actually treat in. And if you do so, this is possible because you can do this with a pretty good precision. The uncertainty from the inverse square law in the ionization chamber, that's actually something that you have to take into consideration. You know, your dose, you're on the depth dose curve, and your dose decreases from the entrance of the source to the exit of the source. And this decrease is about 1.4% in a typical ionization chamber with a diameter of 7 millimeters. This is simply inverse square law. And this is something that you normally correct for by the volume correction, or by a positioning of the source a half of a radius in front of the point that you want to measure. So you can handle this for an external beam, and that's the way you get your data. You measure all the data that you will be using in your planning system, and then put it in the planning system. In brachytherapy, the whole thing is more difficult. We are now in a distance of about 1 centimeter from the source, and so the dose decrease generated only by the inverse square law from the source entrance to the source exit is something like 65%. Let's see, I just want to go over here because I don't see the session anymore. Yes, here we are. So you have this large dose decrease in the chamber. So you actually don't know where is actually the point that you're measuring. This simply gives you no information. You can't correct for these things, but it's difficult, and especially it's difficult to correct at any distance, at any position that you that you need. So this is something in total that is not feasible. So the method is different. Brachytherapy dosimetry is different than that in external beam therapy and dose calculation. Okay, the basic thing, I've already shown this, is the basic number is the reference air camber rate, which specifies the strength of the source. And this air camber rate is connected to the activity of the source, either to the contained activity in this one down here, and what we actually need in calculation is the apparent activity, or the reference air camber rate as it is given in this calculation down here, which does not contain the activity which is absorbed in the source itself. Okay, so now you have this number, the reference air camera rate, and you want to calculate dose. How does this work? Well, our situation is like this. We have the reference air camera rate at 1 meter, and what we want to know is the dose. This is the air camera rate, and we want to know the dose, air camera rate without scatter, dose with scatter, and we want to know the dose at a distance of about 1 centimeter. So we have to perform several calculation steps. First, we have to calculate the air camera rate at 1 meter to the air camera rate at the considered distance where we want to know it. And we do that with the inverse square law. Second step, we need to convert the air camera rate into camera rate in water. So here we have camera rate in air, and we want to know the camera rate in water. See, did my slide vanish with you, or can you still see it? Hello? Can you still see my slide?
Maybe there is a problem.
No,
Okay.
sir. Please share the slide again.
Oh yeah, it clicked off here. It's here. Okay. I think this is it. Okay, we're back. Okay, so we convert the camera rate in air into camera rate in water, and this is done with the mass energy transition coefficients. And not, it's actually it's not what we need is the ratio of the mass air transition coefficients from air to water, or from water divided by air. We cancel out air and multiply with the transition coefficients of water. That gives us air camera rate in water. And the next step is now to transform the camera rate to water into dose rate to water. And this was classically done with empirical conversion factors called Meissberger polynomia. I'll show you what they look like. But these are empirically measured data where somebody measured the air camera rate at a certain distance and then measured the dose rate at the same distance, and then calculated the ratio. And this first person who did it was a fellow called Meissberger. That's why they are called Meissberger polynomia. Okay, so doing this gives you this calculation, this equation that I show you here, and that is very similar to the one I just showed for the calibration of the source. What we want to know is the dose rate to water. We have the reference air camera rate, and now we have to recalculate this, and we do this with we first calculate the air camera rate. Oh, okay. We had the air camera rate. We calculate the. We first recalculate the distance. Reference air camera rate is given at 1 meter. Then we transform this to the distance of that we are looking for with the inverse square law. Next step is to transform the calculate the air camera rate into water camera rate, and that is done with the ratio of the mass energy transfer coefficient of water divided by the mass energy transfer coefficient in air. And then we correct for scatter and absorption with these Meissberger polynomials. Okay, and then there's some small calculations which are actually almost negligible in brachytherapy with the sources that we are using with these high energy sources. Okay, this gives us this equation. That is the way you can do this using numbers from a physics book. And this is actually the way that the planning systems calculated the dose up to about almost 2000. And the newer planning systems now use a different mechanism. That's the TG43. Okay, maybe some short explanations. This is what the Maisberger polynomial look like. They're very flat, but you must not forget that this is additionally multiplied with the inverse square law. So the dose decrease is very steep, but this here is only the correction for the inverse square law that you need to additionally put on there. And these were defined as a polynomial of the distance d. So they look like this. That's why they call them polynomials. And you see these polynomials here for iridium and for cesium, which are very similar. These are high energy sources. We spoke about that yesterday. So they are very similar. And they are very flat because, well, we're in the range of Compton scattering. And what is happening is that the absorption of radiation that occurs in the water, when we travel or when we go deeper in water, we have some absorption, but the absorption is compensated by additional scatter, which comes from the Compton scatter. So these Maisberger polynomials are very flat in a region of almost up to 10 centimeters. So we have almost no dependence on depth. That's different for a low energy source like iodine 125. We have a strong absorption here, so this curve is very steep. So these are basic differences, and we will see them again in TG43. Actually, this is not quite correct, what I showed you. Actually, if you want to calculate the dose at a point up here, what you need to do is you need to actually integrate the dose rate which is coming from the complete source, coming over a long stretch, and which is absorbed in part by the source material itself, by the encapsulation, by the air. And this is correctly done with this equation up here called the Sievert integral, which is a little bit difficult to solve. There are some publications on how to do it, but that is the way you would calculate for an extended source. What I had showed you before is actually for a point source, and that is also why the inverse square law works. So this would be the finally correct way to calculate your dose rate from a brachytherapy source. Something I haven't shown yet is another fact that you have to correct for is the anisotropy of the source. The radiation is not emitted. Is not emitted isotropically. That means if you have your source in the direction as here, a lengthy source like going in this direction, you have and you go to a certain distance, you have a smaller dose rate when you're going along the source than when you're going transverse to the source. So out here at this distance, you have a larger dose rate than you would have at the same distance along the source. And the reason is that the source radiation is absorbed in the source itself, self-absorption of radiation. And this is what causes an isotropy. This is also something that needs to be corrected in a correct calculation. And planning systems used to do that. So, okay, so this is more or less the physical steps that you would use. The practical way this is done is the TG43 formalism, and that's what I want to show you now. TG43 refers to a task group report of a double APM, American Association of Medical Physicists, task group report number 43. This here is the quote, and this where you can look it up in medical physics. And TG43 uses an equation that looks like this here, and I want to explain what this equation is and how it compares to what I was just telling. Okay, this is our equation. First thing we do is, instead of using the reference air camera rate at 1 meter distance, we calculate a new number called the air camera strength, SK. It replaces the air camera rate, and what it actually is reference air camera rate divided by divided by R square. So we make it independent of distance. Now we do a TG43 does a second step. It introduces a new number here, the dose rate constant. Don't confuse this with the air camera rate constant that I spoke about yesterday and at the beginning. The dose rate constant is the ratio of dose rate to water to air camera rate at 1 centimeter distance from the source. And this is a number. This is the basic number. And now this is different than what I just showed you. In the calculation I just showed you, you use the Meissberger polynomial to calculate from air camera rate to source. Here we do this at one point, at 1 centimeter distance. We already calculate dose rate from air camera rate with the dose rate constant. So air camera strength times dose rate constant gives you the dose rate that your source emits at 1 centimeter distance in water. Then TG43 introduces a geometry function, which replaces 1 over r square. And the reason for this is that your source is not a point source, but it's extended. And for an extended source, you have a slightly different, well, the inverse square law is not valid. You have a slightly different law, and I'll show you what this looks like. And then we have another number, which is called the radial dose function. And I wrote here, it replaces the Meissberger polynomial. In a way it does. It looks very similar, but it is different. You may not confuse them. You must not confuse them. It's very important that you really get the correct radial dose function, but it's no problem actually, because TG43 has a good, is used in a very standardized way. So the radial dose function, and the radial dose function is actually very comparable to a depth dose curve after canceling out the inverse square law. So the radial dose function is a ratio of the dose at a radius or at a distance r divided by the dose at 1 centimeter. Okay, and then we also have an isotropy factor, which is tabulated in 2 coordinates. And something you see here is that the TG43 uses a polar coordinate system. I'll show a little bit more about that too. So these are the numbers in the equation, and now I'll show you a little bit more extensively what these things are. So the first thing we do in the TG43 formalism is we place our source in a specific coordinate system, the TG43 coordinate system, and this is defined like this. The origin of the system is at the center of the activity distribution of the source here. The polar axis, let's see, is the polar axis is defined in the source length, pointing away from the source. Yes, this would be the polar direction, and the polar angle is defined between the source length and the line connecting the measurement point to the center of the source. So this gives us our coordinate system, and then we define a reference point at 1 centimeter distance from the source at on the transverse axis of the source, so at a polar angle of 90 degrees, pi of 1/2 pi. This gives us our TG43 reference point. So now in this coordinate system, we can calculate the dose for a point, which is then given in polar coordinates, r, a radial distance, and a polar angle theta. So that's what we want to do, and that's what we want to define our quantities for. So first thing is our air camera strength. I already explained this, or I'll repeat it. the air camera strength is the reference air camera rate multiplied by the square of the distance. So it's independent of distance. And we define the dose rate constant, which is the dose rate at 1 centimeter at the reference point divided by the source strength. And so because of this, the source strength multiplied by the dose rate constant is exactly the dose rate to water at 1 centimeter distance from the source on its radial axis. And this is what is used as source specification, or actually the source specification is the air camera strength. Okay, then we use the geometry function. The geometry function, this here is actually what TG43 used to write, but it's not really quite correct. The geometry function is meant to replace the inverse square law, which is only valid for a point source, to the law which would be valid for an extended source. And what TG43 actually uses are these equations down here, which it's actually what you call the solid angle under which the point here sees the source. For a point source, it's the variation of the solid angle with distance. For a point source, it's simply the inverse square law, and for an extended source with a length L, and this opening, this visible angle here, beta, you get these equations down here. What TG43 is actually using is a law which describes the decrease of radiation fluence with distance for a line source, with a homogeneous distribution of radioactivity along the line. And it's a one-dimensional line source, so it does not take account for the fact that the source is thicker than a line. That's what this is our geometry function that we use. And what TG43 does is at every measuring point, it uses the ratio of the geometry function at the respective point divided by the geometry function of the reference point. So in this way, you have a calculation in which you simply need to multiply the numbers. So yeah. Now this here is what the radial dose function looks like. And you see this is very similar to the ones that I just showed you, to the Meissberger polynomial that I just showed you, but it is different. The main difference you can tell here at 1 centimeter distance, the geometry function at 1 centimeter distance is always 1.0 because it's the dose rate at 1 centimeter divided by the dose rate at 1 centimeter. So that's 1.0. And for the Meissberger polynomials, you would have the air camera rate divided by, the dose rate divided by the air camera rate. And the dose rate is a little bit larger, so you would have something slightly larger, 1.02. In this way, you can tell whether you're looking at a radial dose function or a Meissberger polynomial. And this is what they look like. Again, this is for let's see, which one is it? This is for iridium-192. This middle one is for cesium-137. And this one on the bottom here is for cobalt-60. So you can see that they are also very similar. These are small numbers here. This is, the differences are not very large. And that is the reason why the dose distributions for cobalt and for iridium are actually very similar. It's there's not much difference in these numbers that you use to calculate. It is very different for something like iodine here. There you have a very steep radial dose function because of the fact that this is produced a low energy source, which is mainly governed by photoelectric absorption. So you have a very strong decrease This diagram on the right shows you the same thing, only at a different scale. And I've changed the scale here so that I can show you the inverse square law here. So this is, well, an approximation maybe for our geometry function, but you need to multiply this curve here to these curves to get the depth dose. So the depth dose dependence is actually dominated here by the inverse square law, and not as much by these by the radial dose function. That's actually only a small correction. Okay, this here is the anisotropy again. It's a factor. The dose rate at it's always calculated as the dose rate at the considered point in relation to the dose rate at the same distance on the transversal axis. Important thing is that the dose TG43 factors are all calculated as ratios of absorbed dose to water that can actually be measured, and that's actually what has happened. They have been measured, and they've also been calculated by Monte Carlo calculations, and that's where this data was generated. And the geometry factor is always canceled out at every position, so that it is reused in calculation. Think about that a minute. It's not that difficult. Okay, so what TG43 now does is it delivers. It has published data in data tables. The data is tabulated for actually almost all of the commercial sources. You can find this data, and you can find it in databases that are published on the internet. I'll show you where that is in a minute. And the original data is always tabulated in a polar coordinate system in 2 dimensions, r and polar angle theta. And something you may find if you look into the data is that there are also tables in Cartesian coordinates, x, y, z, or x and y. These are not supposed to be used for dose calculation. They are only supposed to be used to verify dose calculations. They're made to be used to calculate the dose from one single source at a certain Cartesian coordinate in water. So you calculate it in water with your planning system and compare to these long and away tables. And that gives you an information how exact your calculation in your planning system is. That is what they're supposed to be used for. To do dose calculations, always use the tables in polar coordinates, even if then you may transform the polar coordinates into Cartesian coordinates. Okay, and you get information of the radial dose function from about 1 millimeter to 10 centimeters for seeds, and from 5 millimeters to 10 centimeters for afterloading sources. Not any closer, there things become uncertain. The data is determined from measurements and Monte Carlo calculations. It is reviewed by the high energy brachytherapy working group. Sorry, this slipped away here. That's a working group of double APM and Estro, which examine these data, and then they decide which are the best data, the most valid data, which is normally a mix or a compromise between measured data and Monte Carlo calculated data. So these are best values of the data, so-called consensus data sets, and that is what is published on the internet and is recommended for clinical use, and that is what your planning system uses. So if you want to check if your planning system is correct, go into the internet, look at the TG43 data for the source that you are using, and compare that to the data that is tabulated in your planning system. So they're published on the website of the Radiological Physics Center, RPC, of the AAPM, which is cited at the MD Anderson Cancer Center in Houston, and this is the website where you can find the data. No, this is a website where you find a list of the sources for which consensus data exists, and then from there you get a link to the databases, and the databases are here on this Canadian database at the Carleton University in Toronto, or at a database, the Graphics database at the University of Valencia in Spain. So this is down, these two sites down here are where you can actually find your data. TG43 is not too bad. It calculates with an uncertainty for high energy sources of around 3.4%, and for low energy sources like iodine 125, 4.4%. So that's pretty good. And these are two publications which show you how this uncertainty was found, or how these numbers were generated. So this is actually pretty good. But something you need to know is that TG43 has limitations. And the main limitation of TG43 is that it calculates in pure water, and it calculates in an it calculates in an extended body of water, actually in in a very large phantom. The phantom that they use is something like 60 by 60 by 60 centimeters for calculation and for measurements. And the dose that you actually get in a patient is dependent also on the size of the patient, on the size of the phantom, because you lose scatter radiation when the patient is smaller. So this is one point in which TG43 cannot be correct. And the second thing is it calculates in pure water. It takes no respect of any kind of heterogeneity, like a bone here. And that means that the calculations of TG43 are actually what you see here on a CT based dose planning is actually only an overlay of a calculation in water in an infinite. That's the number I was looking for. TG43 calculates in an infinite water phantom. So what you see is the overlay of a calculation in an infinite water phantom onto the CT image, and it doesn't take into account any of the heterogeneities, which also means that on a slide down here with a lot of artifacts, it also does the same calculation. So that's maybe one little advantage. This does make a difference, and this is what this slide shows here. I have to look at time a little bit. What this shows is the dose is a depth dose distribution of an iridium source. On the left side, the source is placed in the center of a water phantom, of a water volume, and on the right side, at the surface of a water water volume. And what is shown here is the dose as it builds up from primary absorption and the buildup of scatter dose. And this sums up to the total dose. And what you can see on these diagrams is that the primary is exactly the same when your source is at the surface, but the scatter is much less. So your total dose is also less. And this table shows you here how much it is less. And now your source is at the surface of the water or of the patient, and now you go to at 1 centimeter distance from the source, and there you find that the difference is not so very big. It's something like 1.4 centimeters. At 5 centimeters, it's 11%. And if you go 15 centimeters away from the source, you'll be somewhere down here. and the difference is 41%. So this can make a very large difference. But you have to keep in mind that in one place you are always applying your dose close to the source, so you will hardly ever be farther away than 5 centimeters. Where for one source you have a difference of 11%, but you're not doing your dose calculation with only one source at 5 centimeters. You have many more sources which are at shorter distances. You're always using a large number of dwell positions, and most of them are closer to the point that you want to irradiate here than 5 centimeters. So your sum miscalculation is comparably small. You're not doing too bad at all, but you do have some differences when you're at the surface of the patient, where the formalism does not take into account the scatter losses out into air. So these differences are important if you use, for instance, shielded applicators, because in shielded applicators, your planning system will normally have some kind of a transmission factor with which it reduces the dose which passes through the shielding. Just if you don't know it, this here is what a shielded applicator looks like. You have these tungsten shields here that you can place. This here would be the channel in which these are vaginal cylinders. This would be the channel, and then you place the shield onto the channel, and then you put the cylinder over on top of that, and then this gives you a shielding in a certain direction. Like here, it's shielded towards the bottom, and you have no dose at the bottom, and you have full transmission through the top. So this is how it works. Planning systems calculate this dose here to the shielded direction pretty accurately with a transmission factor. Where the differences are larger is here at the edge of the shielding. Oh yes, here you can see where how only a quarter of the dose distribution is cut out. Here at the edge of the shield, where scatter plays a large role, this is where you get some miscalculations with TG43. Okay, again, this was to show you that another thing that TG43 does not take into account is the dependence of the dose rate on energy and material mainly. But as we saw on the radial dose functions, the calculation is still pretty exact, accurate, because we are in the range of photoelectric, of Compton scattering, and only for the low energy sources we are in the range of photoelectric absorption. So this does not cause such a big problem. Here again was the definition of the high energy sources, for which TG43 calculates correctly, where we have low energy dependence and low material dependence, and low energy sources are mainly dominated by the photoelectric absorption, and you have a high dependence on energy and on material. And medium energy sources like ytterbium, which I showed you yesterday, are a mix of Compton and photoelectric absorption, which changes with the distance from the source in water. Okay, so for high energy sources, TG43 calculations are generally okay. For low and medium energy sources, we actually need better calculations. We can still use TG43 for low energy sources, because what we do there is we normally don't treat in heterogeneous media. We treat from tissue, the prostate, to another place in the prostate. So we're not crossing any heterogeneity, and therefore the tabulated values are still pretty correct also for low energy sources in things like seed applications. Okay, but Actually, we need better algorithms, and such algorithms are now being introduced into the planning systems. You can buy them; they're expensive, and I'll just want to fly over 2 or 3 slides, which show you that they are actually it's a very large effort to commission these and to verify that your system is working correctly. The algorithms that are used right now are separation convolution algorithms, like the collapsed cone. By the manufacturer, it's called ACE, or the grid-based Boltzmann solvers called Accurus by Varian. And there are also some systems which work with Monte Carlo calculations. The differences between Monte Carlo calculations, or between model-based algorithms and TG43, are actually small. They're only large, for instance, at the patient, larger at the patient surface. You will get slightly, you actually receive slightly lower doses than TG43 calculates, and in a dense material like a bone, you will get a higher dose than TG43 calculates. So for experimental work, you can use the model-based algorithms. They are still in tests. I think they're not really, they're not that ready for clinical use. I believe Renata Walter is going to show you more about model-based algorithms tomorrow. Anyway, there is literature in which you can inform yourself on how the model-based algorithms work. And if you do decide to use model-based algorithms, you must look into this literature and see what the recommendations are. And some of the things that you need to know is that these some of the models, for instance, do not calculate in dose to water, but in dose to medium. So you have to recalculate dose to water, what you want to know from this dose to medium. Also, so you know how to do it, and you also need to know you also need to know what kind of an uncertainty you're adding with this. And some of these algorithms, especially the Accurus, the grid-based Boltzmann solver, does not use CT numbers, Hounsfield numbers. It uses material composition, just like protons do. So you need to transform your data, your CT data, into material compositions. Okay, this here is TG43 again, TG186, this report, and these here are 2 reports which show how the commissioning of a model-based algorithm is supposed to be done. I'll skip the rest of this. Okay, and I can summarize with this. TG43 provides the basic calculation formalism used in present treatment planning. The data is available on the internet. The formalism can be applied to all commercial high and low energy sources. Its limitation is that it calculates in an infinite water medium and does not consider inhomogeneities, shielding, or missing or add additional scatter radiation due to the calculation of that you would have in the infinite water medium. New algorithms are in development, and to use medium energy sources like ytterbium, we definitely need these new algorithms. Okay, now I had planned to say a few words about dose measurements. I'm over time already, but I still would like to show you just 2 or 3 points and the rest I think you can look up on the slides yourself. The main thing is already summarized here in these remarks on this slide here. Any kind of experimental dose measurements, measuring with an ionization chamber or whatever in brachytherapy, these measurements have large uncertainties, and they are difficult to reduce. It's difficult to reduce these uncertainties. So experimental dosimetry is normally not a practical thing for clinical use, for clinical verification, to actually measure what your patient is getting. And it has only very limited use for in vivo dosimetry. It's simply too uncertain what you measure. Any dose measurement you do must be carefully planned as a physical experiment in a simple phantom arrangement. And you can use it, for instance, to calibrate sources. That's what I just showed you at the standard lab. Or for research work. And a typical kind of research work would be to measure TG43 parameters like the radial dose function and the anisotropy function. And anything else, I think you should try not to do, because the uncertainty is simply larger than any information that you want to get out of the measurement. And just a short fly through what the reason is. The reason, again, is the steep dose gradient, which means that you need an extremely high positioning accuracy. You need to position both the source and the detector with an accuracy of something like 1/100th of a millimeter to get 2% or 2% uncertainty. This is simply inverse square law. Or at 5 millimeter distance, 0.025 millimeters. At a centimeter, it's still 5/100ths of a millimeter that you need to position both source and detector. So this is something that's very difficult to do. You need exact positioning. You need detectors with high spatial resolution. You need a small sensitive volume of the detector so that you don't have too much volume averaging. You need to know the exact position of the effective point of measurement, and your detector should be isotropic. So this goes through different other things. You need a large dynamic of the source, because high dynamic range, because you have large dose, steep dose rate decrease. You have large differences in dose rate close to the source to the dose rates at a few centimeters. The detectors must have a small energy dependence. You're always working with spectra of sources which change in the source, and you always have this composition of total dose and primary and scatter. You have changing spectra, so you need a small, so your detectors must have a low energy dependence. And okay, this slide shows the energy dependence of certain detectors. And so the last thing I'd like to show here is what are possible candidates for brachytherapy detectors are small ionization chambers, even though they do have quite a large dose averaging. But for certain things like measuring the radial dose function, they can be pretty good. TLDs seem to be pretty good. Radiochromic film can be good. One thing you need to know is you may not use radiographic film, silver or silver halide films, the ones you used to use in radiography. They are not useful because they have too large an energy dependence. And one detector that is coming up that seems to be interesting for brachytherapy is a microdiamond detector. And I think that was about all I wanted to show you for dose measurements. So I think that was it. Thank you for your attention. And do you have any questions? Oh, maybe one thing I'll show you is that at the end you'll get handouts of this. At the end of the slides, there are always there's always references where you can look up the things that I mentioned in the slides. The references are normally always given, or they given at the on the slides at the images when I speak of something. And there also I would also give you some recommendations for textbooks. Like the important textbook for physicists in brachytherapy is this book by Dimos Baltas, Sakeliou, and Samboglu, The Physics of Modern Brachytherapy for Oncology. This is something anybody physicist working brachytherapy should have on his desk. And you should also look at, well, okay, introductory reading, pretty good, is the IAEA syllabus, or a book here by Jack Estrow that you can download from the internet for free. So this is something you could look up, these two books. You can also get the IAEA syllabus on the internet. And okay, international standards, some additional reading. So now I think I will actually quit and wait for your questions. Thank you very much.
Thank you, sir, for your very knowledgeable and informative talk.
Let's see. Yeah, let's.
Now we can pick up some questions.
Mhm.
So my first question is from Asad Yusuf. Why we don't measure activity, instead measure karma?
Well, that was the point that I explained in a little bit more extent yesterday. If you want to use activity, you must always use the air camera rate constant, this gamma delta that I showed you yesterday, to convert air camera rate into or to convert activity into air camera rate. And that means that you are adding additional uncertainty, because there's a lot of uncertainty, or more uncertainty in the air camera rate than in a direct measurement. It's simply because you have to multiply numbers with an uncertainty, and that therefore it's not recommended. And okay, today we're working with TG43, and TG43 doesn't even mention activity. It only uses the source strength, which is air camera rate. Is that okay?
Okay, sir. Now, second one from Salih Osman. Why we use current reading instead of charge?
Pardon, I didn't quite understand that.
Why we use current reading instead of charge?
No, I still didn't understand that. Is it on the chat? Why we use current rating instead of what? Current reading? Or I didn't understand this acoustically.
Okay, we can go in T1. T1 from Asad Yusuf. Why inverse square law not applicable?
Well, the inverse square law is actually only valid for a point source. For anything that is extended in space, for any source that is extended in space, you actually need to sum up, to integrate the inverse square law from every position in the source. And that gives you a slightly different distance dependence than inverse square law. The farther you go away from the source, the better it works, because your source appears to be more like a point source. But when you get close to the source, and that's where we're working in brachytherapy, you actually notice that your fluence, your dose rate, decreases different than 1 over r square, and it is described more correctly by the geometry function, which is given in TG43. Is that okay?
Okay, sir. From our participants, Suresh wants to know, in the current system in dose calculation, we are using TG43 with no heterogeneity correction.
Yes.
In a situation where we use contrast for bladder, delineation in treatment of a CS cervix, how it affects the bladder dose evaluation?
It won't make much of it. It won't make much difference in your calculations or in the information that you get out of the calculation. The error that you make is not that big, even if you use something like contrast. The dose to the contrast, of course, will be larger, but you're not interested in that. What you want to know is the dose to the patient, and the dose to the patient is well, you will maybe get a little bit more scatter radiation, but these are small differences. They will be within, well, 1, 2, 3, maybe less than 10%. I would imagine. I think Renata Walter is going to show you more about these uncertainties tomorrow in her lecture, and you will see that it's actually only very few situations where you get noticeable differences between the TG43 calculation and a more exact calculation with one of the model-based algorithms. One main reason that heterogeneity corrections are important in external beam therapy, because in external beam therapy, we are always irradiating from the outside of the patient to someplace inside, and then we are passing through the heterogeneities. So if we pass through the lung into the mediastinum, we have much less absorption in the lung than we would have if this was solid tissue. And that is something that we will really need to take into account. In brachytherapy, we are almost always irradiating from one place in tissue to a second place in the same tissue without any heterogeneity. And for this reason, anything that we do in brachytherapy is not really affected much by the heterogeneity. And the same thing would be valid for the bladder. When is bladder dose of interest? Maybe if you're treating, would be treating bladder tissue, and you would be putting your sources in the bladder tissue. Okay, but then you would be irradiating from bladder to bladder, and the contrast would be somewhere on top of somewhere in the bladder, somewhere a little bit farther away. And the only thing that would affect this is the scatter radiation coming from there. But the place, if you have performed your implant correctly, the place that you want to irradiate is very close to the source. So this the contribution of the scatter coming from the contrast is small. It's not enough to really make a big difference. And if you're irradiating something like gynecological, like a cervical cancer, and the contrast in the bladder will be 10 centimeters away or 7 centimeters away, so who cares? The contribution is so small that it doesn't make any, hardly makes any difference to the dose. Would that answer the question? Anything?
Okay.
I don't see anything popping up here.
There are no more questions. Thank you,
No
sir.
more questions? Okay, if you have a second of time, I could. Oh, yeah, I'm off screen again. I could show you the X-ray source that we spoke about yesterday, the Zoft source. Maybe this is something that you didn't. That you are you interested in it? We can leave it too.
Yes, sir.
Folks.
Thank you so much for your informative session.
Okay, thank you.
Skill and knowledgeable lecture has helped all the participants learn. I'm very happy to spend a valuable time with you. I want to extend warmest thanks to you, sparing your valuable time and knowledge with us.
Yes, thank you very much. It was a pleasure, and I'll look into the next lectures too.
Yes, sir. Thanks to all the participants for their active participation in the program. I'd also like to thank Dr. Ghulam Abu Zakaria, founder chairman of SCMPCR, and the entire team of SCMPCR, whose tireless efforts have made this program functional for us. Thank you everyone once again. We appreciate your presence here. We'll see you next lecture. Our next lecture is on 7 February 2021 on brachytherapy dose calculation.